Let's move on to section 2.4, Ampere-Circuitial law. That's the second Maxwell equation. This equation is a combination of an experimental finding of Ørsted that the electrical current generates magnetic field. So it's simply just electrical currents and the magnetic field. So Ørsted found out that you can electrical current can produce magnetic field. If you move a compass near to a current carrying wire, then the direction of the compass will be changed because of the presence of magnetic field. Second is a mathematical contribution by Maxwell that time-varying electrical field give rise to magnetic fields. Okay, so the contribution of Maxwell is according to his derivation. The equation shows that time-varying electrical field produce magnetic field. Okay, from the Faraday's law, we know that time-varying magnetic field produce electrical field. And here, the Ampere-Circuitial law gives you another relationship that is time-varying electrical field. About time-varying electrical field produce magnetic field. And the combination of the two, the combination of Faraday's law and Ampere-Circuitial law will produce electromagnetic wave, because time-varying electrical field produce magnetic field, and the time-varying magnetic field will produce an electrical field, and so on and so forth. So Maxwell predicts that there will be a phenomenon called the electromagnetic wave due to the combination of the two equations. Unfortunately, Maxwell died at the age of about 42, even though that he had made a lot of scientific findings. He unfortunately didn't observe, didn't see the proof of electromagnetic wave. So as you can see here, he died at the age of 48. All right, he's a native he's a Scotland native living in Edinburgh， 爱丁堡人呢，对，爱丁堡人，苏格兰人哈。然后 this is the statue you found in Edinburgh, okay? And Maxwell was well known for talking to his dog about his scientific findings. So since the dog understands Maxwell equation, there's no reason that you guys don't understand it, right? 这只狗还蛮可爱的哈，在这里也有哈。那普罗莎手上拿的那一个是那个分光盘呢，也就是什么？你把一个陀螺上面一半涂红色，另外一半涂绿色，然后你把它转，它就变大变色那个哈 ，OK。所以那个马斯韦尔他的其实那个年代18世纪那个年代的科学家都是多才多学的哈，他们其实都是跨领域的哈。所以那因为你用雕像来去呈现 Maxwell equation 好像不太容易了哈，所以他把他的另外一个发明哈，也就是这种分光调色盘的方式刻在他的那个雕像上面 ，OK。所以这个是他在光学上面的贡献哈。Alright, so let's compare the Maxwell equation, the Faraday's law and the Ampere-Circuitial law. So So in Faraday's law, we know that the closed loop integral of electrical field equals to the minus of time derivative of magnetic flux. And for the Ampere-Secchio law, we have this. So you see, left side of the equation are similar. It's also a closed loop integral. 应该是 I 吧。B 还是用什么方式给 D？ So again, the right side of the Ampere-Secchio law have two terms. One is current. And current is what? Current is the direct source of magnetic field. According to Oerstar's finding, as long as you have a current, you will produce magnetic field. Similarly, as long as you have charge, you will produce electrical field. Okay, but we will talk about the charge due to the electrical field due to the charge in the third Maxwell equations. So we leave it later. And so here is a time varying field. So time varying magnetic field produce electrical field. We know that time varying magnetic field produce. What is the significance of this? It's EMF, electric motive force, but it's also the equivalence of voltage, right? Which is also referred as the electrical potential. Electrical potential. And what is this physical indication of this thing? When this thing tells you directly this is current, so this thing will be current as well. And this thing will have the same unit as current. So the physical implication of this thing is what? It's current. It's ampere. Its unit is ampere. So this is the physical current, real current. Well, I had to use the term real current because, but it's probably easier for you to understand. I here stands for current, real charge movement, such as conducting current in the wire, or the convection currents on. 我 check 一下，这是 LED 灯管还是真的日光灯管？我们先，这个应该是真的 LED 了哈，现在已经很少真的日光灯管了哈。只要是真的日光灯管的话，它里头叫做 low pressure plasma， 低压电浆啊。日光灯管里头，它其实是一个低压的电浆态的阴离子、阳离子那当它的那个离子的那个能量在那边跳来跳去的时候，它就会发光所以在日光灯管里头的电流是移动的阴阳离子所以那一种电流称之为 convection current。就是 convection current，convection current。那我刚刚讲到的另外一种 current 叫 conduction current， 那个是在导体里面的电流基本上是电子流了conduction current。然后，那请问半导体里头的那个电流是哪一种？半导体的那个 PN junction 的那个电流 比较像 convection current 它有移动的电动，其实混合在一起的啦，有电子流也有电动流嘛，好，那这个比较容易理解，这是真实的电流，这个呢，它的效果等于什么？电流啊，我们排在一起了嘛，所以这个东西是它的效果等于电流，但这个东西是什么东西？这个东西是时变磁场，对不对？时变电场，这是电场嘛？这是对时间的微分，只要它对时间的微分不等于0，它就是效果就等于电流 ，OK？ 事实上，这个东西所以这个东西我们在课本上的名称叫做 displacement current。它没有真实的电荷移动，但是它的效果等于电流。第一次听到这个东西吗？物理有听过 ，OK， 好。事实上你们都学过这个东西了。对啊，电容啊。所以你想想看，在电容里头，所以电容中间是什么？我们最常见的平板电容，它中间是一个什么？绝缘体啊。所以绝缘体有没有电荷移动流过？没有嘛。但是你在开关的瞬间是有电流通过的嘛？因为你知道电容是什么？先通后断嘛，先通后开，先短路后开路之类的 ，OK， 电感反过来所以当你在状态改变的瞬间，这里头虽然没有荷流过，但它的效果等于有电流。那它的效果是怎么产生的？因为你在电容充电的瞬间是发生了什么事？在这里头的正电荷越来越多，负电荷越来越多，所以在那个 moment 那个当下，它的电荷它的充电，当然放电也算嘛，在充电的过程当中，那电荷越来越多，电荷越来越多的结果是什么？这边的电场越来越大，电场越来越大，那就表示什么？你的电场对于时间的微分不等于0。当你的电容充饱电的时候，也就是它的上面的正电荷跟下面的负电荷不再变多或者不再变少的时候，它的电场有没有？有，但它是维持一个定值，电场还是在那里嘛，但是它的电场的量不会再变多或变少，那就表示什么？那一个 displacement current 它的电场的时间微分等于0。所以 displacement current 就等于0，所以这个现象其实在你的电路学里头已经早就有经验过了 ，OK， 所以时变电场的效果等于电流，所以时变电场电流会产生磁场，所以时变电场也会产生磁场，那另外一个再注意到这边的式子，你会看到这边同样是 time derivative， 时间的微分，这边呢都是 spatial variation， 空间上面的变动。不过这一个现象我们要到第3章讲 Maxwell equation 的 differential form 差分形式的时候会更明显，所以你会看到在 Maxwell equation 里头，它的左右两边其实是有它的意义的，左边是 to the left is the spatial variation of electric and magnetic field, and to the right are time variation of electric and magnetic field. And the Ampere's Kirchhoff law provides you that this is the fundamental, the current is the fundamental magnetic field source, the fundamental source of magnetic field. And the displacement current, the time varying electrical field is the secondary magnetic field source. And the Faraday's law tells you that the time varying magnetic field is the secondary source for electrical field. Okay? So, however, the equation shown here is a little bit awkward because it involves some properties that we haven't defined yet. One is mu sub 0 is the so-called permeability, 介磁系数。Permeability. And epsilon is the so-called permittivity, 介电系数。The subscript 0 means the permeability in free space in vacuum and the permittivity in vacuum. And in general, the magnetic flux divided by permeability can be defined in terms of H. H is the so-called magnetic field intensity, 磁场强度. So it's similar to electrical field intensity. And epsilon E is defined as displacement flux density, which I tend to call it electrical flux density, similar to magnetic flux density. So we can replace this and this as electrical flux density and magnetic field intensity, so that the two equations there are more energy analogy between the two equations. So it looks a little bit more symmetric. All right, so here we can define B over mu sub 0 as the magnetic field intensity H, and B, which is the product of epsilon sub 0 times E, is the so-called displacement flux density or electrical flux density. One thing that need to be noticed is that the magnetic force direction is perpendicular to the moving direction of electrical charge. So they perform no work on the electrical charge. So the magnetic field, because the direction of magnetic field are perpendicular to the direction of charge movement, so it changed the as we have seen in the discussion of Helmholtz force. Helmholtz force, the electrical field will perform some work on the moving charge, while the magnetic force only change the direction of the moving charge, but provides no work on the moving charge. Okay? And so, similar to the electric motive force, which is the loop integral, closed loop integral of electrical field intensity, the closed loop integral of magnetic field intensity is referred to as the magnetomotive force, magnetomotive force, 磁动势, as shown here. So another adjustment about the equation is the current. So as I mentioned earlier, the current I, which is also labeled as IC, C stands for conduction currents and or convection currents. So you can also call that they are real currents. The currents can be line currents, surface currents, or volume currents, according to the the conditions specified in the problem. But so a more general way to put the currents is to put it as the integration of current density across a specific area. Okay, so that. This is I. Okay. 所以电流一个更 general 的一个方式来去写它的话，就是把电流写作是电流密度的积分电流密度的积分。So, well, so it can be written in this form. 我怎么没有找到比较喜欢的样子？OK， 这个了。So the more general expression for the ampere schedule is in this format. The closed loop integral of magnetic field intensity equals to the surface integral of current density and the time derivative of surface integral of electrical flux density. So the magnetic motive force equals to the sum of real currents and displacement current. I don't know if this equation reminds you of anything, but let's go back a little bit to see an important property of this equation. So this illustration tells you that the magnetic motive force, that is, the closed loop integral of magnetic field intensity around this path equals to the time derivative of electrical flux density across this surface, as well as the real current flows through the surface. And one important thing to be remembered is that the currents always forms a loop, right? The currents always form a loop. There is no end for our currents. And because of this property, we have an important result from this derivation. Let's see. That is, the magnetomotive force around a closed loop is a unique value, which is the sum of the real current and the displacement current. So let's see how can we prove this thing. So here we have space which can be divided into two surfaces. The two surfaces will form a closed surface. S1 and S2 forms a closed surface, 就像一个蛋壳一样。那S1 跟 S2 刚好就是蛋壳的左半部跟右半部。那这个缝呢，在这个就像你那个什么转蛋嘛，扭蛋的那个蛋壳，然后中间那条线就是这边的 contour C1 跟 C2。So C1 and C2 are the contour that divides the space into two. As you can see here, C1 and C2 are of opposite direction. So the direction of S1, which is bounded by C1, is pointing to the left using the right-hand rule. And the direction of S2, which is bounded by C2, is pointing to the right because of the right-hand rule. So if we join the two spaces together, here we try to prove that magnetomotive force is a unique value. MMF 是一个特定值是一个特定值。So we try So here we first write the relationship of H on C1 and D on S1 first. So this is the magnetomotive force accumulated on contour C1, which equals to the time derivative of real currents flowing out of the S1 surface and the time derivative of D, of integration of D flowing out of the S1 surface. And you can also write another equation for C2 and S2, like equation 2.18b. And if you sums up the two equation 2.18a and b, you end up with a 0 on the left. Why? Because the C1 and C2 contour are the same, they are only different by the direction. So the line integral over H on C1 and line integral over C2 are of opposite signs, okay, so they cancel out. And to the right, you have S1 plus, you have surface integral of current density on S1 and S2, which forms a closed loop, closed surface. You have time derivative of displacement flux density on S1 and S2, which is also on a closed surface. So that will be the total real currents flowing out of this volume and the total displacement current flowing out of this volume. And what is the implication? What is the significance of the result of this equation? It tells you that the total currents flowing out of this closed surface is 0, which is consistent of a basic theorem that we learned a couple of years ago. That is the Norton's theorem. The Norton's theorem. For in the electrical circuit, for any points on the electrical circuit, the total current flowing out of the node is 0, right? Now, this is the current flowing into the node, and this is the current flowing out of the node. Their sum equals to 0 in all time. Now, that is the Norton's theorem or Kirchhoff's law of current, KCL. Okay, now. All right, so goes back to the case of capacitor. So we know that in the capacitor, when it conducts currents, but there are no real currents flowing in the capacitor because you have an insulator between the parallel plate capacitor. So the currents, the effective current is the so-called displacement current. So if you draw an imaginary closed surface around this region, you have real currents flowing from left to right, and they end up as charges on the two plates. And the displacement current will flow from the inside of the surface to the outside as an equivalent current, so that the total currents flows in and flows out of this closed surface is 0 at all time. All right. So in this case, we have conduction current from the left and the displacement current to the right, and they are of the same magnitude. And for this capacitor configuration, because you can simplify as the electrical flux as D, the surface area of the parallel plate capacitor is A, then the current I shall be equal to the time derivative of D over A. So because A is a constant, so you need to have a time varying electrical flux density so that you will have a current. And once the capacitor is fully charged or fully discharged, then you will have no current for the capacitor. All right, so combines the two. So we know that the displaced current will take over in the previous case. The displacement current will take over between the two parallel plates. Okay, so and now let's summarize our finding in these sections. The combination of Ampere's Security law and Faraday's law tells you that time varying electrical field and time varying magnetic field are dependent, are interdependent. They are not independent 两个是不是独立的十变电磁场、十变电场、十变磁场是耦合在一起的，它们是相关的，它们是绑在一起的，绑定在一起的，它们不是互相独立的所以这个是至少你今天要了解到、体会到的一件事情。十变电场跟十变磁场是绑做会的它们不是互相独立的OK。好，那最后我们这些我们有看到了就是那个电磁波的产生了假如你有一个上下振动的电流的话，那根据右手定则，你就有磁场。然后你看到为什么这边是点点，这边是叉叉？因为这边的叉叉是在比较之前的时候产生的，那个时候的电流是朝下的，所以它产生的是左边的叉叉磁场跟右边的点点磁场。那在之前一点的时候呢，那个电流是朝上的，所以这边是点点，这边是叉叉所以这个现象就可以看到它的那个，因为你的那个交流电流上下震荡，所以它的磁场也是一下是顺转，一下是逆转然后随着时间的推演，它可以往外传播所以这是电磁波的产生。那当然我们常讲的一句话就是磁生电，电生磁啦就可以从刚刚的安培电路定律跟法拉第定律来去观察到。OK， 好了，我们今天到这边。